here's my expected output, what was my actual, and I want to run this thing in a simulation. So the root abstraction that we'll talk about through here is just a thing that contains optionally some state, logic, and then we'll talk about purity and side effects and things like that a bit later on. But given an input or given a starting state, when something happens, a trigger happens inside of the system, let me model what I think should happen or happened or should happen, or let me test to see that what I expected actually happened. Some types of system formalization, formalisms. This is the first one I talked about, the discrete event simulation. Differential equation system specification. So diffeq is continually variable. These types of systems allow you to express functions and edit and update the parameters going into those functions and be able to simulate continually variable systems like power flow through wires or speed of object moving in space or something like that. The DTS, discrete time system specification, is kind of a derivative of that. The idea was it's really complex to reason about and correctly model the algorithms in one of these DES models. And so if we treat it as a system that samples that continually variable thing, then I can reason about these individual points within the space, and I can do more interesting things with them. So an entire field evolved outside of that. And then more recently, someone came along and said, well, this has discrete events, but there's also these start and stop signals. It looks a lot like an analog electric current. And we can actually say that these trigger points are these discrete events, but instead of representing like a continually variable system, they might be able to represent events in the real world, like a thing happened, or a user clicked on something, or someone pushed the accelerator on the car by n degrees. And so it's again a slightly different way of visualizing the DTSS model. And it has evolved quite a bit. So in 1976, people realized that there was some kind of relationship between these modeling options. And these have been formalized, so there's tables that talk about what kinds of things fit inside of each of these categories. And as these relationships got defined, they came up with rules and mathematical and heuristic rules that help you determine how these systems interplay. And it got more complex in the 90s, and in 97 it got even more complex. And the book goes into the details of each one of these things, what its kind of origination story is, how it's evolved over time, and then what, again, really fascinating to me if you're working in a simulation system type environment, it gives you examples and tables and rules to follow, semantic rules to follow that are mathematically rigorous, embedded over this 40-year life cycle, so that you can apply that into your software logic and not try and reinvent the wheel. What I've found a lot when I've tried to work with actor models or people implementing distributed systems is that they are guessing at like pieces of information that they just aren't familiar with yet. And it's very easy to miss little edge cases or nuances when you're translating between models. And so this gives you it's dense material, but if that's your space, it's really good to read through that stuff and start thinking about the thought processes that have gone on from these experts for 40 years. So that's my rah-rah for those models. I'm going to dig into this one called devs. There's a guy named Tushar. He looked at the discrete events, and originally it was conceptualized as a manufacturing system. It's a set of things that operated one on the tail end of the other, machines, progressing over time through varied states, where each of those state transitions is represented by a discrete event. That's why it's called a discrete event system. And it also expanded on some ideas of set theory. It expanded into mathematics. Like functional programming takes some stuff. It can be used to describe some of these things with its orientation around set theory, left folding, set-based operations, and things like that. And I think I flipped these slides around because I meant to say there's too much stuff in all of them, so I'm going to jump into devs. So that's why I got mixed up there. Questions, thoughts so far? Should I have brought copies of the book for you guys to peruse through?
I always take a free book.
Yeah, right.
I guess I never really considered a discrete event in that way, because in past life I dealt mostly closely with hardware, and you're more about sampling, and you see it more apparent that you're doing, different samples of, it's not a continuous, a discrete sample versus events, which when you go over to application land, it's like, oh yeah, click, that just can't happen too fast, so I never really put the two together in the same picture.
Yeah. And along those lines, is that's one of the things that occurred to me as part of reading this, I had a sense of it before, but you start looking through the sampling sets, and what are you doing in analytics post-processing systems often? Is you're looking at relationships between samples or patterns across time in samples, and often you're saying the processor spiked by n percentage, therefore alarm sounds. And I'm like, oh, well, that alarm trigger in that monitoring software is essentially a translation point between the sampled system and the discrete event system. And so now from the output of one system, so I've got this like continually variable system that's being sampled into this other system, and then the sampled system is actually now producing discrete events. And then discrete events, if you take another abstraction off of that, what do you think of this is just the way that I visualize things, sequences of discrete events plotted together as a timeline almost form a sampling set of the state of the system, and you can start looking at that back again in another model, and then derive new events off of that, and this like loop, a recursive loop of analytics. It's like super fascinating how that stuff composes. But yeah, that's awesome. So you did work at Dell. Do you do work now in the same space, or?
I've moved to Linux application microservices.
Oh, cool.
But to support the same radio product, basically. So I've gone from where I'm looking at the baseband communication and generating, looking at samples, signals there, generating notification, which ends up in a messaging system, a database somewhere in America.
Fantastic.
So
it's very cool. Does this apply? The theories around this are probably very familiar. Is anyone else in other industries?
Yeah, I have some background in this. I got my doctorate in systems biology.
Okay, so you know way more about this than I do.
Well, I know a lot about this little thing that I did. But we had a system we built that models biochemical reaction networks.
That's awesome.
And so, you'll have a cellular process, like say you're breaking down sugar and creating ATP. So that's a pathway, and it's a network of biochemical reaction networks, or biochemical reactions. So what we do is you build a model for the biologist, and then you attach a diffie-q to, or some rate function to each of those reactions. And you can track where your participants in those reactions go over time. So we built a simulation platform for those biochemical reaction networks in another database just to kind of store those models. And then we use Mathematica to simulate the network. So it's kind of, I just looked today on Meetup, and like, what's going on? I'm like, oh, let's see what's going on over here. So.
Nice. Well, welcome. Yeah. That's one of the reasons why I wanted to be involved with this meetup, because obviously this is an area of interest to me. But I find that I tend to be high skill in one area, like dev and data. But getting out into the field and talking to more people is how I've learned everything I know. So that's awesome. I'm glad you guys came.
Me, I'm more on the operations side of things, and architecture, system stuff. Most things. I like the parts that you're talking about as far as alerting and notifications and stuff when the system is reaching a threshold, or that's definitely right up my alley right now. So.
Cool. Right on. Bring a scooter. So I went rogue and I bought an office scooter. And the rule is that if you ride it around, you have to leave it in another spot somewhere in the building for someone else to pick up later.
Yeah, you have plenty of room to
Oh man, it's great. These concrete floors are amazing. So this section on theory, it gauged to the audience. So I delivered a variant of this topic to another audience. And you guys are probably a bit more advanced than what they were at. But this is kind of some of the stuff that I start to think about when applying the systems level thinking into software development and architecture and the kind of problem spaces that we have in an enterprise. And so this is kind of a hit list. It's semi-organized. And so we'll go through all these things, and if there's time at the end, we'll try and get to that one. And so this is the point I made earlier. We're already using simulation tooling. So like connect this back to things that you are already doing and already familiar with, and it'll expand your viewpoint of it. And like you said, unit testing is one of my canonical examples. I like to point to that. But some of the stuff that I realize people don't consider a simulation system is like non-production clusters. So what is our QA system really? Ideally, it would be a simulation of production. And why do we want that to be the case? Well, so I can test hypotheses. Does my system actually function? Does data get stored in the right place when I execute this interaction on the interface? So that I can have more confidence that when I go into the real world, into my production system, that still functions. And the same is true for things like Selenium. I'm trying to isolate bits of user interface. I'm going to exercise them in very controlled ways, test theory. So this applies to a lot of the stuff that we do. So I think it behooves us to be more familiar with this kind of thinking, this kind of thought process. One of my personal mantras along those lines is single responsibility. So you get into unit testing, and what is a unit? But it's a very small-grained piece of functionality or behavior. And that can apply to different parts of our system. And this is where the levels of system modeling kind of comes into play. So you can get down to the little bit of function code level. And then as you start organizing these things into clusters or hierarchies or different structures, we'll kind of get into that a little bit later on. The unit is now different. And so this is kind of where unit testing diverges a bit from the systems theory stuff. Is that unit testing, I'm trying to test the function. Systems at the systems level, I want to be able to do kind of like end-to-end or integration tests across a more complex graph of actors. And I want to be able to still have the capability of modeling that accurately and testing hypotheses against it. So I start with, at each layer, I want the organized unit to have a single responsibility. Now, it might be composed of different pieces, but the composition itself, I want to try and trim down to a single unit. Like, the purpose of this layer is to coordinate messages between the other two things composed below it, right? For example. But not to, and then communicate this over there and put something in the database and fire it off an email. Like, you want to keep these things contained. And redact out any details that are not directly compatible with the thing they're trying to accomplish. Another interesting side effect that happens from that is that it starts identifying cross-cutting concerns, and I can start looking at my systems one step away from them and start thinking about how can I separate the definitions of the core business value, the places where I'm actually trying to derive unique value and data out of, versus the things that just have to happen in the background in order to support my runtime. And there's a lot of different runtimes out there. You might be talking to Cassandra, you might be on a network, you might be going across threads and talking to memory. Is there a way to conceptualize systems of logic and data manipulation in such a way that we can apply that same system potentially in multiple different runtimes? Modulo some edge cases and gotchas, but the better job we can do of that, the easier it's going to be for us to say, have a dev runtime system that can emulate my production system so that I don't have to have so much infrastructure in place for running basic operations, for example. Dive a little bit into object-oriented programming. So the thing that occurred to me also is that my mental shape of what an object is roughly looks like my system composition diagram from before. It's got like things that you can trigger, inputs that you can put into it by calling methods or updating properties or things like that. So there's some places where it diverges in my mind, and that's what I was trying to represent with these, is that like references to other things that are in process or that are directly linked. There's all these side effects and cross-cutting concerns that are not visible there, and so we kind of take them for granted. I don't know if any of you have ever tried to write decom or corba, distributed objects, and run into how hard it is to make object-looking things work in a distributed, disconnected graph. And I have worked on those things. It's been a while now, and I've moved away from that because of the pain points, and that's kind of early days of what led me down the direction of thinking more along like how do you solve that problem? And maybe it's I don't use object-oriented programming to represent this aspect of my system, or I think of it a little bit differently. Some things about object-oriented programming, but this is the core of it. You can use object orientation to provide supporting computational mechanisms. So as long as you're thinking about if the end goal is being able to describe the simulation system, and your abstractions are oriented around that, the modeling piece of that, then you're not using objects inside of the units. You're composing them in an object graph, if that's tracking at all. So I can use objects to represent the set of tasks that are executing. I can use objects to track state across a graph of interacting tasks and delegating and dispatching data through those things. And what I'm thinking is that maybe I don't want the OO concerns to leak inside of the systems, the definitions, my custom logic pieces, but it's fine to use them as describing the framework in which those things run. And in fact, it's really powerful, and there are existing, let's see, where was I talking about that? There's a bunch of, so there's a bunch of existing frameworks that you can use, like TPL libraries, actor frameworks, Actix in Rust, Akka in .NET. So those kinds of systems get you some of the way here to varying degrees of success in my mind. Is that tracking at all?
So you're saying that basically you're using objects to define the scope of your system.
Mm-hmm. And to describe the internals of an instance of the runtime, for example. And it sounds very abstract. In practice, what it means is that you have dependency-injected gates that move things across a network pipe, because you need to transmit data back and forth across the network pipe. But when that data gets transmitted in, you've abstracted out the actual moving of the data so that your atomic units of the system definition of how the data flows through the logical gates and the data manipulation gates is separated from that network-related concern.
The purpose being like an isolation tool?
Mm-hmm.
Yeah.
You can think of it as like, so if I'm trying to test, does this process work? Is the data manipulated the proper way? Do the signals flow through my business logic the correct way? Does it trigger the correct subset of actors in my graph? That's what I care about. Do I care that in this particular runtime there might be a network transmission issue? Like when I'm ultimately at runtime, I definitely care about that. And so is there a way to tease apart the definition models that I use in these two spaces? And OO generally doesn't feel aligned with the definition of the process and the state transition logic pieces for me. But then you can still build the runtime using that model, and it doesn't impact your ability to reason about these things in a disconnected fashion.
So we're pulling apart side effects from pure functions.
Yes.
Okay.
Totally. And that's another point where I have a slight bias toward functional programming, but I'm also object-oriented programming has some legit frameworks that serve the purpose well. But you have to be more disciplined, I think, to hold the line and not cross into the dangerous aspects of OO programming within your system definition. And for some of those reasons, and I've got some stuff coming up on that. Okay. Hey, welcome. So, all right, so you have to tell us your favorite breakfast cereal.
Wait a minute. I've seen this before. I don't have one. I don't eat breakfast cereal.
That's a great answer. You win the prize. It was a trick question. There is no spoon.
I was going to say pizza, but
I don't know if that counts as a breakfast cereal.
Yeah, well, if you tear it into little pieces and you pour milk over it.
That's called salt, right?
Yeah, let's take a quick pizza break.
Cool.
Thanks, man.
Looks good.
Get my Troy weed going on.
From a 1930s, like, film line.
Exactly. So we're
I should introduce myself. Object. I used to work with independent policies.
Yeah. And that, oh.
Well, add another 45
Hi again, people on the interwebs. I think this is my first official Twitch stream.
Well, I actually,
Yeah.
I don't know how.
Very nice. Welcome to the world.
I feel so millennial now all of a sudden. So during the break, so it was pointed out that there's an example of an existing system that one of the members here was talking about where they have, in fact, an OO modeling side that's driving their user interface and the execution runtime, and is actually handing stuff off to a functional backplane to do the data crunching and the data manipulation and business logic rules. And so, yeah, that's exactly what I'm talking about. Like your runtime might be easier to model using standard OO, best practices, object-oriented design patterns, everything. Like, go nuts. Just in my experience, when you get into the data modeling side of stuff and the simulation side of stuff, where you want things we'll talk about in a bit, like purity and immutability, and kind of like be thinking in that model, the functional programming in an OO language or a functional language tends to fit better there. Another point that comes to mind related to that is that if your entire process space can fit on a single machine, then you can use OO modeling to do that pretty effectively too. In my experience, when you have to decompose systems across multiple computers, then functional thoughts around data and data manipulation tend to fit that distributed systems paradigm a bit better. And so I tend to, again, turn to functional languages or functional aspects of object-oriented languages for those pieces. So it depends on how big your scale is. So like if we're running a production system, I want cap theorem stuff. So I want availability and partitionability. So I'm going to think of it a little bit differently about how I define my runtime to be able to handle scaling to a larger volume or scaling across regions and things like that. But as I said, the production system and the QA systems are all simulations of the real world, and so I like to be thinking of those kind of the same way that I do unit tests and other systems abstractions. I don't know if any of have any of you ever heard of the programming language called Elm?
Yeah.
So this is a quote from the main guy in Elm. It says, "Make impossible states impossible." And so that's just like a little nod. If you're interested in that stuff, check out that link. The idea is to model your data sets in a way that you can't, you don't have system exceptions. You formally express the error that happened as another active entity in the system. So like you emit a message saying that failed, so that you can respond to the error as a signal itself through your simulation. And so there's some interesting stuff there. You'll see some more Elmy kind of things a little bit later on and references to other, if we have time. Do we have a hard time stop on? Great, so midnight is good with everyone? Fantastic. For functional programming, and not necessarily like, again, it's not language thing, it's just concept stuff. We want to be thinking about side effects, the notion of what purity means, and I want to talk a little bit about some thoughts I've had around monadic composition that I think applies to the systems design piece. And we'd love to get your thoughts on that and some feedback on it. So side effects are, here's our systems model, right? It's our box, but we've induced something that runs outside of our system and creates a non-deterministic behavior. I went reference something off the clock, I put some data into a database somewhere, and I don't know, I can simulate that it failed to actually write onto the platter, but like in the runtime system, that's a bit of the hidden part of the system. And so how do I account for those things? How do they affect our software systems? What are some strategies for handling and accounting for side effects in applications that we've built? And then how does that translate into when we're thinking of like trying to do simulation systems? How do we handle side effecty type stuff in simulation systems? Do you guys have any thoughts or experience to throw out there related to side effecty stuff? Have you experienced the pains of side effects ever?
Oh yeah.
I think we all have. Any program that's useful has side effects.
Oh, but so like the perfect Haskell program produces nothing but heat because it has no inputs or outputs. Totally. You have to have side effects in order for a system to function. So it occurred to me like, so an example of a physics simulator, like a particle engine, right? It's a simulation. It fits into the context of a lot of stuff that we've talked about. It models rules of the physics engine, gravity, wind shear, collision, all of this stuff. And you set all of that up, and then at the very edge, you put in your side effects. And the side effects create interactions and potentially create other side effects, but it's operating through this simulated environment. And so the way that I think about that is how Elm or Haskell or some of those functional programming languages have chosen to solve that problem is to kind of push the side effects out to the fringe of the system as best as possible. And object-oriented programming has a similar kind of approach to it. Dependency injection, DI frameworks, aspect-oriented programming is the notion of trying to maintain purity within the inner bits and compose as much of it together as possible. And then when I need to, so I can do my unit testing and I can put mock stuff in and a controlled environment that I can actually run the simulation and test against. But then at runtime, I swap it in for the real world and hopefully catch all the chaos that ensues. So that's been kind of the strategy, is to push it out to the fringe of the system. And so then when you start thinking about how do we describe a system and compose those systems into larger graphs of systems, how does that side effect management strategy scale across compositions? So that's some of the stuff that I've been trying to think about, and hopefully we'll get to that stuff too. Peer system, I think you guys probably know all this stuff, is something you can execute the same function over and over again, you always get the same result. There's no side effects in there. It's really nice because it's reliable, it's deterministic. And so again, that's why we push the side effects out, so that as much of our system as possible is deterministic. Monetic composition. Has anyone ever seen railway-oriented development? Familiar with promises and futures? So I've got a little toy library that I was writing in Rust to describe how, like, a railway-oriented composition around an abstraction for systems and sinks. And so I'll try and talk about that in a little while, but I wanted to seed this slide in case there was anyone that's not familiar with this. Has anyone not seen this, or does not know what I'm talking about here? Yeah. So the idea is that in a single function, I have like a single input produces a single output, right? And so when I'm starting to talk about systems composition, I have more complex interactions between things. And one of the ways that I've started conceiving that is that, like, so if this is my system definition, I can have multiple channels to emit signals out of, instead of a single return from a function. So it's a very similar process. I create one signal coming in, and I can have one or more signals coming out. So but conceptually, it's kind of like having a multiple return from a function call. Okay? But it's composed a little bit differently, and by composing it differently, it allows me to take inputs across these three things and say, if all three of these succeed, then that's success up here, and if any one of them fails, then that gets routed down and becomes the fail here. So I'll try and go more into that in a little bit. Yeah, but so there's like kind of two different styles of composing and organizing systems that I've seen. There's hierarchical single process simulations. It might be closer to like having the OO runtime sitting in front of it. And there's some implications to how you connect these little discrete units together in a hierarchical fashion that works inside of a single process. And I haven't thought of a really good way to translate that into a distributed process. But there are other strategies for dealing with things in a distributed space and doing composition across these entities. In distributed space, it seems to work pretty well, but adds unnecessary complexity in a single process space. So what do I mean by hierarchical system decomposition? So I've got my basic shape of the system unit that we talked about, the inputs and state and outputs. And inside of that box, I have multiple instances of those, and I can wire them together to encapsulate, again, atomic pure functions inside, and route data down through. And sorry, I'm trying to see if I've lost anyone getting. No? Okay, cool.
These S is
yeah,
state?
Please.
What is that?
Yeah, S represents the state internally. So some things that I thought about related to this is that the higher order specs are easier to reason about. When I get down multiple levels in here, I could be working with dozens or hundreds or potentially even thousands of actors or units. And so wrapping those up inside of encapsulation and stepping up that layer of system composition allows me to reason about a simpler piece. And so now the inputs are going to be a redacted set, a smaller set. It's easier for me to think about and reason about. And I can walk that up. But it becomes more precise as I decompose it down into these little pieces. So I've got this kind of this pressure between I want to decompose things into the smallest unit possible because of single responsibility. It's easier to test. It's easier to run in its own isolated environment. But it's really hard to reason about thousands of those things. And so what are some strategies for organizing the code in a way that developers can look at that and reason about the structure of those things and how the data flows? I've got a sample that I'd like to talk about and get your thoughts about on that. And then what tooling might you put in place to make those things easier to reason about? So there's another piece of that. Some examples of single process systems that you guys have probably heard about. Redux flow, the React JavaScript runtime, the Elm runtime, which one is that? That's the Cycle.js runtime. Does anyone recognize a commonality between these things? Circles. Data flows. So often what they have is a state, that's the S inside the box. They have signals that are coming in to manipulate that state. There's outputs that go out into the reducers and update the UI, and then it just goes in a loop like that. And so looking at those things can help you think about the single process hierarchical composition systems are modeled in each of these things in slightly different ways. So there's not a one canonical way to do it, and there's a lot of really good thought that's gone into the system, that's gone into this space. And I don't know if it was interesting to you guys, but I saw the commonality across those things and saw how it kind of correlated to the systems composition models. And it was like, oh, okay. What they're trying to solve for is how do we decompose user interface graphs and hierarchies in a way that developers can still reason about them and then compose them back up into full applications. Oh, so that sounds actually a lot of what I'm trying to do in the systems design world. And so what things can I leverage from their syntax and their compositional structures and their runtime models and their execution models and all of that. So nested composition has nodes and leafs that compose it together, and here's one example of how that might operate. So I've got a structure that is the current state. I've got a couple of a command, which is the input signals. And I have events, which are the output signals from that. So it evaluates the command and determines whether to send an event or an error. So that's our pattern is I evaluate a command, and depending on my business logic case, I'm going to emit in this channel either an event or an error. That's pretty straightforward. I have apply that allows me to take the current state, apply an event that has happened, and then it creates the update. And in this case, it's a mutable operation because Rust is nice about mutation management. So how would I compose this structure together across, so if this is a system, like a unit, how would I compose it together? So I'm thinking about what are the component pieces that are involved in describing this, and it's got the configuration, which is variations of execution runtime. So I can set some limits, for example, in this counter example. So I can have multiple counters running on the same operational model here, but I can vary that input there. And so all I've done here inside of this thing is basically the purpose of this is to compose across two other actors or two other systems. So that's the single responsibility thing, is composing those two bits. And so it just captures the config, the state, the commands, the events, and the errors. Once I've got all of that stuff, the next step is to say, okay, well, here is the application of that is to, so my job is to describe, this is the set of commands that I can do, which is increment, and the set of commands for each of the counters that I'm composing across. And then the right one for the set of commands that I'm composing across. And in here, when I go to apply it, I can evaluate and look if it's the left one, then I route it to my left actor, and if it's the right one, I route it to my right actor. This is pretty trivial, and this is not complex code. It's not complex theory at all. But this pattern, as far as I can tell, composes up complex application stacks. So if you break things down into this subset of things, it appears to handle variadic environment parameters. It handles state manipulation and everything except side effects. Does anyone have thoughts or questions about this piece of it? Is this like super low level? Is this too easy? What is the context here? Do you guys see a context between the theme and this piece of?
So the expansion maybe is a bit foggy, but I mean, as you're saying, building this into a complex system.
Okay.
I mean, I think I follow, but an example might be interesting.
Okay. Yeah, I'll try and come up with a more concrete, tangible example then. So when I had the decomposition node where I'm taking the graph with two subcomponents inside of it and encapsulating over the top of them. Composed across, and notice that the pattern of the hierarchy is expressed in the code logic that delegates down into the constituent pieces, the application of state updates that delegates down in the constituent pieces, and the composition across all of the subcommands that are being routed around.
But the subcomponents there don't know about each other, so you're
Correct.
just orchestrating what happens at a higher level for those components.
Yep.
So they still remain doing the same exact, they're just scale. That would be like a load balance in there.
Yep. Exactly. Yeah, maybe subsequent events, we can get synced up on this again and have more dialogue around this. Again, one of the reasons I wanted to present this is because you end up talking in a bubble, and I want to get this is super fun because I got people who actually know the space and have real world applications of it outside of my experience that it can ping stuff off and help me refine my way of expressing it and communicating and thinking about it. So just throwing stuff out to you guys. Cool. Here's another one. This is back to the book again. This is a formalized version called RDEVs, which is routed discrete event systems. And so when you get into this model, it's specifically talking about kind of distributed systems theory and how do we route events across disparate groups of agents or systems. So the RDEVs formalism is based on devs and defines a set of devs atomic models that use routing information to do various things, like authenticating senders and receivers and transactions to route messages down to the subgroups. The end result of RDEVs is essentially an expansion of what we just looked at, which is an in-process single hierarchy explicit delegation. This would be running in an operating environment where something else is receiving the event signals and, say, dispatching it out to the set of actors that want to listen for that kind of event. And so how do I translate from the single process to the distributed process? And the cool thing is, again, there's 40 years of knowledge and examples and formalisms built around that conceptual model. So if you're trying to learn about this stuff, don't look at me, go read the book. This is just my book review. Let's see, so message dispatching and many other concerns are expected to be handled by the underlying runtimes, not the systems themselves. Those are the side of this cross-cutting concerns, the set of things that, like, if you think about it, it doesn't actually affect what I'm trying to operate on. It's just an artifact of the fact that I'm running inside of a physical network, and there's hard disks, and there's computers and processes and threads and all of that stuff. So I want to separate those things out. And you're probably going to need some kind of hub subsystem. In the example we just looked at, it was function dispatch, so it was pretty low level, but that could just be throw it off to Google PubSub, or throw it off to a Kafka stream, or dispatch it over Istio to a named pipe through service discovery. But ultimately, it doesn't matter which one of those we choose. We just need some capability to identify where the other things are that care about the message that I've got, the signal that I want to dispatch into the space, and then make sure that it happens. And there's an ongoing question. I've got some thoughts around this. It'd be really fun to talk about with you guys some of the ways that you've modeled this. We talked a little bit about persisting data in, I think it was like in memory or maybe on disk in the local environment where the simulations are running. What other strategies might there be for data aggregation or partitioning and storage in a distributed simulations setting?
You can use an object relational bridge to use a relational database. So we use OJB. It's part of some Java APIs. And so you use a relational database to store your data about your system. Okay. Usually these were the parameters for a model. You can store states there too, and then use that bridge to extract your data out for your objects, populate your objects with the parameters, and then.
Okay. Yeah. So you're doing like a dehydrate into relational database, and then when the next signal comes along, you rehydrate out of the relational database, and then run your next round of simulation in that model. It's probably not going to fit in here, but one of the topics that I'm really fascinated with is, has anyone heard of Microsoft's Arleen's platform? So the whole notion of ephemeral actors was really fascinating to me. I liked like a lot of the properties and scalability aspects of it. There's a plugin for that for CQRS and event sourcing that allows you to do ephemeralized actors with persistence layer baked in. So if you guys are into event-oriented systems, and likely you're into event sourcing, and I'd love to have another talk either hosted by one of you guys, where I can attend and we can have dialogues around it, or a roundtable type setting where we can talk about those systems. And that goes into how do you so I've got this runtime and I'm dealing with side effects, and now I've got to persist the state of this somehow as it evolves, persist the state of what's happened in those side effects, and then if you're dealing at the scale that we're dealing with billions of dollars worth of transactions, how do we deal with the transaction volume of stuff coming in? So you have to start thinking about partition spaces of data coming in and routing across to different runtimes, because you have to think about capacity theorem and being available to that many people and still fitting within SLAs, and it gets super complicated. So I have my theories in the practice that we're trying to put in place, and kind of some of the stuff that's still arrived here, but how do you deal with that in a complex simulated system? One of my favorite topics in the world.
Key-based storage might work to some degree, right? So same idea as hydration or whatever. I mean, and then you have a key that would be representative of the data.
Yep.
Some.
Yeah. So you break down the state of each, like the identity of each instance within your simulation, and that becomes a key that you can persist off. And in event sourcing, you can give it the list of all events that have acted on that instance, and then that gives you like this dehydration and rehydration process that can be done in a highly partitioned, highly ephemeral way, similar to Arleen's, but like Arleen's distributed system, not just Arleen's cluster single execution. So key value storage is a key piece of that, I think.
What was that?
And I think you're dead on. Is that the key value primitive is the underlying root of that.
So ephemeral, you've been using the ephemeral language.
Yep.
That one. Okay, so by definition, it is temporary. So this would be within that you want to define when you're talking about SLA or whatever. I mean that would be the definition of what you expect ephemeral to do, right? Like how long lived it is, or whether it actually is it eventual delivery, or is it right? Yeah.
So when I said SLA related to that, I was thinking of the expected return, expected like latency bounds and volume of requests coming in and availability of the instances themselves.
Okay. Yeah.
Does that make sense?
Yeah.
Okay.
But the ephemeral part.
The ephemeral part. Are you familiar with like the Akka runtime or like the in-process actor models?
Yeah.
So you build that system up, and then through execution, it mutates the state of the actor system itself. And then the challenge is, okay, say I need to turn this system off and turn it back on again, and I need to be able to resume where I left off. How can I safely serialize the entire state of that graph and then rehydrate it back into that same state in order to continue processing new events. I'm like, oh man, that's really hard. We've been trying to do that for a long time. And so I have this theory of what they did in Orleans, and the reason I call it an ephemeral actor is that they have the cluster running, and if no one's making any calls, the system goes through and basically garbage collects all of the runtimes and turns them all off. And then a message comes in that says this is related to player 1, 2, 3, 4. And so it'll go out and it does a gossip-based protocol to determine which node in the cluster is running player service with aggregate 1, 2, 3, 4 subkey. And if there isn't one, then it triggers a launch. And it goes and it says, okay, find an open node, have that node go to my event store, load all events related to player 1, 2, 3, 4 stream, left fold to create state, and then take the event in, apply against state, and determine output, and persist output. And now you can kill that process. Because if another signal comes in, then you just rehydrate it out of the event store. So it's a really interesting load balancing metric, because it means that your hot actors, your hot instances, end up living in the cluster longer and are already state loaded as of the last state, because it guarantees that it'll only route to one active instance of that name subpartition within the cluster. So take a look at Orleans. It's really fun. You can spin up a cluster inside a Docker environment and poke at it. And there's some UIs that you can throw on top of it and kind of observe what it's doing. And it's interesting getting some of the .NET stuff running inside Docker containers sometimes, but you got it running. The more interesting thing to me was, how do I apply that conceptual model to cloud infrastructure and highly distributed key value stores? And be able to realize ephemeral actor model on top of distributed key value store, which is kind of what I'm implying here. Is if I describe I had the hierarchy before, right? That's the picture and the code example that we muddled our way through, and so could I take each of those different subsystems, the individual unit pieces, and augment them with just a little bit of metadata to say, oh, here's your name and here's your partitioning scheme or something like that. And then take that and have defined my business logic, my data manipulation, my simulation system in such a way that I can run it inside a console and poke it with values through the CLI and exercise it in a simulated local environment, and then take exactly the same graph that I was just manipulating and recompile it with metadata to deploy into, is anyone familiar with Istio and Kubernetes? So deploy it into a Kubernetes cluster running Istio, and use the metadata to go and add routing rules into the Envoy router, have Ambassador set up, go and register endpoints with Ambassador to set up a gateway, and now clients can call in signal player 1, 2, 3, 4 message X. X gets routed through Istio, and then gets persisted down into Cloud Bigtable, for example. And now I could something along these lines. I could have an Orleans style operation model. The whole reason I wanted to point this out is because it reinforces that separation that I'm trying to figure out how to properly communicate. So I'm trying different ways of expressing that mental model to you guys to get dialogue going on it. But this is another thing. So if I could take that model, run it in an object-oriented runtime environment, run it in a console, and then deploy it to our cloud infrastructure and run it up there, that would be pretty cool.
So the automation tools around all this is the key.
Yeah. So I want someone to build that for me.
GitLab is actually putting out something called Menlo or something like that. A new service that's built around data science that is essentially doing what you're talking about. It deploys to multi-cloud, whatever.
Fantastic. Would you mind going to the meetup and posting a link to that?
Yeah, no, I can't. Yeah.
Cool.
There's not a lot there, but I found something.
Okay. Well, I'll hold you accountable to all 1,000 people watching on the Twitch stream right now. So you get a lot of Twitter love if you get it done, and
Right on.
Let's see. Evaluating technologies, consider how we might decouple the technology from the purpose of the system. So things to discuss. We've been kind of discussing that point a bit already. does the processing paradigm you have in mind consider various topics from the presentation that we talked about? So like in your models, in your real world runtime, have you run into things that look or feel a bit like this? Does any of this seem useful at all? Does it like adjust the way you think about it, or you already thought that way? And
we don't do a lot more. We do use the sub-hub system, messaging base, and we're moving to a Qubit dispatch router, which will create a new set of problems because the persistence and having the connection have to be there.
Okay.
And mesh network, but we don't reconstruct objects from data that's in messages or key stores. But we do spin up new instances in the OpenShift environment to not continue the conversation, but because we're routed, we can get things. So it's very interesting to rebuild an object from that data. Something we really haven't exercised.
Yeah. At scale though, that could be pretty expensive, right? Because you have to, that SLA part's pretty interesting. Not how you're saying it, but in reference to how quickly you'd have to have that available.
to be able to bootstrap an environment like that.
Right, so at scale then it would be.
Yeah, like so we were doing some work with Kubernetes and Helm to apply Helm charts out to our infrastructure, and we've got like a lot of CI/CD tooling built around immutable infrastructure concepts, and so it feels nice to be able to say like, here's my template of what I want my system to look like. Can you please Helm apply and have my cluster actually look like that? You know, pretty reliably, modulo any errors that come out of Helm and stuff that you have to figure out. But you know, once you get that for the most part worked out, now you have this much like reduced stress and anxiety about making changes into QA and production clusters. And so the question I have about like about manually curated routes and dispatchers and pub subs that don't have this meta model that is backing them up in a Helm chartish kind of way is what is your operational cost of having someone know how all that stuff is supposed to be configured, having it like manually dialed in equivalently to your testing contexts, and then applied accurately in dev and other like cross-team collaboration environments so that you get that consistency. So like I'm trying to think like how could we get a Helm apply style interaction model onto our service bus, our routers, our you know, containers, our Kubernetes Istio mesh network, whatever it is under the covers.
Yeah, that's actually a problem I'm solving right now. Currently, railroads have a topology-based system. And we're going to where you can just tell us, these are the applications, say my locomotive control computer that needs to join a network, and these are the resources, the wayside arms that are in the inventory for BNSF, which is a railroad. And then we will make all of that addressable in mesh network.
Okay.
So you can get away from having that everything is pre-configure address, and then you know, if you look at the topology, usually the overlap to make sure that something is double, triple covered by an endpoint manager. There's a lot of things that go through right now to get a working system. So that makes things like software upgrades very complex because you have to coordinate what goes down first, second, third type of thing. Moving to a different platform is what I'm doing.
Yeah, that's the complexities of snowflakes, like recreating snowflakes, making more cattles. Those are the pets versus cattle analogy in Docker containers. Can you blow away your infrastructure and have it reform itself? So what you're talking about is like an auto load discovery thing, where when the service comes on, it calls into a system and it auto configures itself so that it's findable on the network and all of that. That's a good model. I also like you mentioned the gossip protocols. I think someone over here maybe mentioned gossip protocols earlier.
That is me. It's really like a bad distributed systems joke.
No, it's an awesome one. You can't go wrong with gossip protocols. Auto configured member sets and things like that. What are we doing on time? Do we actually have a time limit on here?
You don't.
Okay.
Basically, when you want to be done, or you just want to have nothing but conversation or something, then I mean it's.
Okay. Yeah, so like, I'm trying to bounce. I don't feel a strong need to go through all of the slides in the slide deck, so I'd prefer to just have conversations until people are like, all right, cool, it's time. It's like 8 o'clock, let's go home or whatever. Or we can open it to discussion. Trying to think of what else I've got in here. I wanted to talk about time. It's one of those side effects that is hard to manage, like data persistence. If you don't have, so like if you're working with physical time, that becomes a side effect. It's non-deterministic. Every time you ask for it, it's going to be a bit different. And it's really hard to write simulation systems that depend on the real wall clock time, because now any of the variances or nuances of where time impacted the execution of the graph becomes like hard to test. Not necessarily impossible, but it certainly makes it harder. So in a lot of places, it's easier to implement a simulated time so that you can, right, you see this in things like reactive frameworks where you have, like in the unit testing space within the reactive extensions, for example, the ability to inject time pieces into messages as they flow through the reactive extensions runtime. And so and you can also emulate alternative time semantics. So you can create long jumps through time. You can do incremental, like monatomic style updates down to milliseconds. You can emulate same time, even though the simulation's running through real time. You can do really fascinating things. So there's a couple different event time representations. The book goes into talking about time, because time is one of the interesting components of these continually variable systems. Like continually variable is variable through time. T is like one of the common things across all of the modeling types. Like obviously there's other side effects, but time is a big one. I'm not going to dig into this, but I just wanted to put it up there, mostly because for the audience that I was originally presenting this to, it's a point of reference, so they take the slide deck and say we talked about time, and I can go in and look at what is discrete event time and how is that different from simulated time, and oh hey, cool, someone has thought about, like similar to that the system component models and how they translate back and forth between each other. Someone has thought about how all of these different time representations can interleave with each other and interact with each other using kind of formalized mechanisms. So you get it more likely to get it right than trying to make it up yourself.
One thing about that is that might be interesting is like isolating that time piece. So I've had to deal with that data, specifically around Cassandra actually corrupting things, becoming unhealthy because of latency between two different entity servers, right? Yeah. So if you separate that and isolate them so that, for example, in this case, you want to stay in a relatively close data center versus shooting off into, say, like Georgia versus Virginia or something. That even that small space can still create a latency that can cause you trouble. So in other words, your system will look at an NTP server that you're running in that VPC versus using Amazon's NTP servers, right? So
totally.
That can help with that, because otherwise it's going to be tough to.
Well, here's an advantage of modeling your stuff using the simulation systems theory. Right, so I have a real wall clock time that I depend on for grabbing timestamps. I can plug in a simulated time that gives me intentionally stretched bounds across time, and then model those in a distributed system to see what happens when and then hook up a real Cassandra server on the back end, and then have it dropping like intentionally bad timestamps in there and see what my edge cases are in the distributed system space. So like by having crafted that composed model and pushed all the peripherals out to the outside and having the pure functions in the middle, I can now do things like drop one of the side effects in place and then exercise it in a controlled environment. Yeah, that would be really fun to see how that plays out. Time in distributed systems is really a pain.
It was ugly.
I was going to say you should do that.
I should do that?
That's fun. Managing
time in distributed systems, or build the simulation model?
Do the simulation.
Yeah. Oh, it's wicked. I've seen some of the what's his name? The Jepsen tests that have come out of that stuff. It's brutal.
Oh yeah.
I also really fascinated by what they did with Spanner as a so instead of trying to solve the problem, we're going to brute force our way through it, And how can we do that? Well, let's put atomic clocks and GPS positional things on every piece of infrastructure in our entire enterprise. And then we'll sync, instead of having to coordinate across an NTP server, I can have really, really fine-grained, low delta resolution across data centers. And you're like, okay, well, what's my maximum spread given this technology? It's like 7 milliseconds or something like that. Okay, that's a much smaller bound than any network latency can ever achieve consensus on. So what can I do with that? Well, if I delay my reads beyond 7 milliseconds, then I can read my writes. Ooh. So if I just like hack the system, I get a pretty fast distributed relational database where I don't have to, where I can give immediate consistency in a geo-replicated space. It's bonkers. You should read the papers on that. It's really cool. But time, it's hard.
For one example that I know of, a time-related problem that was solved is like Bitcoin.
Oh yeah.
You have distributed ledger, and so that's your call that your distributed system. And each node competes to solve some arbitrary math problem. And the one that does it first is the one that says, okay, this is the next block in the blockchain. And that's used to solve your kind of a time problem, because that node was the first one to compete to make the change to the ledger, right? And so that gives you at least a linear, first in line, first in time kind of solution for a distributed system.
Yep.
So it's doing some, energy intensive computation as a cost, and then that gives you a probabilistic kind of distribution of, who's using so much computing power or whatever, and then they can make the change.
Yep.
And it's all done.
Yeah, and you take that forced delay of n amount of time, and then you change the complexity setting to keep it approximately 10 minutes.
Yeah.
And then you say it's only really settled after it's been 6 rounds beyond that, and it's the even more inefficient version of that 7 millisecond offset. It's like 30 to 60 minutes offset, and then you have confirmed read to write on a distributed consensus. Bitcoin is cool like that too. That's a great example. Yeah, all right. No, go for it.
We had to mess with the simulation of time for leap second and leap second announcements. And
oh man.
Because we're doing base band communication, and the base station has a synchronized frames for everyone in the system or nearby. And I don't think we were ready to test that. And the fact that the GPS chip has to get the announcement for for when the next leap second occurs, because it's not on the calendar. It's whenever some guy says, "Yeah, we're gonna have one in a few months."
And I had to do software one time that mapped multiple calendars across each other through time zones with clients and operators, and it's just like, it's such a nightmare. Like Arizona, it is part of Arizona that doesn't have daylight savings time, and the rest of it does. And then another part that has 30 minutes instead of an hour.
Wasn't there another state that just decided it wasn't going to do that anymore, too? Or it was going to get rid of the time change?
Yes.
And so
we have to have the technocracy revolution that eliminates all time zone changes, unifies across a common model for all time zones.
So the China model.
Yeah, pretty much. I think we should all do that.
I don't particularly disagree. I still say we should use the Star Trek model because it's more accurate than our actual time.
I just want to point out to everyone online, Adrian thinks that we should go to the China model. It's official.
I also think we should use metric.
Oh, that's too far.
Yeah. I mean, like half the country does.
Someone cut him off.
Let him.
It just barks root beer.
It's got bite.
It does.
Time is so much fun. So at some point, distributed systems meetup, we need someone to come in and do a talk on time and how time impacts distributed systems, and maybe examples in a couple of them. And he'll talk about Cassandra and how it deals with time.
Talk about how vector clocks are easy.
Oh, vector clocks are so easy. I had a slide in here for vector clocks and I hit it because it was like, that's too off topic. I can't go there.
I just have one little point to add about the Bitcoin example is that, like, I guess the idea was because wall clock time can be forged. You want to make a transaction, right? So you submit a transaction to the network. And let's say that somebody wants to do that transaction but beat it out to do a double spend or something like that. I guess they wanted to get rid of wall clock time because who do you trust as an oracle in a distributed system?
Totally.
So I guess that kind of completes the point that I was trying to make earlier.
No pun intended, right?
Yeah. Use Bitcoin. Don't use what was it, the centrally managed ones. Anyone that has an oracle in a crypto space, danger. Okay, so sinks and systems abstractions. So I was trying to think of what an abstraction would look like in code for organizing the systems, that diagram, where you had a single input signal triggering potentially multiple output signals. And so I just want to talk about the concepts, introduce the semantics in my mind of the sink, and some of the system definitions in code, what that looks like. So sink is the thing that receives incoming events. Doesn't know where they came from, doesn't know if they're buffered, doesn't know if they're ordered, doesn't know the semantics about it. Because we have single responsibility, all it knows about it is the data that it expects to come in on that sink channel. So it lets us hide the implementation of how those events are processed by the receiver or who the receiver is. So like when I dispatch something, I just say, like, send it, because I got this signal, I looked at my state and my logic, and I said, well, here's what you should do. And whether it goes out to five other actors or none, or gets persisted or not my concern. Now it's bounded in a testable space. Okay, so that's cool. I also want to think about composition. So that's that railways-oriented development thing. How can I take those discrete units that have, dispatching channels and ingress channels and compose them together using something that looks like the magnetic composition model from a functional programming space. So it came up. This is Rust. Sorry if it's not familiar. The semantics translate over to like an interface in Go or C# or something like that. Or in fact, did I do that? I did it. Oh, I translated it in C# just for you guys. I forgot I had done on the slide. So it's a function it's a thing that implements this interface that has a method called send that you give it an input and it gives out a result. And those are generic parameters. And result can represent now, and there's an example of this in that prior code example I showed, where the result can actually compose across multiple signal channels. So I went over a couple different compositional options, and this one felt the most ergonomic. Whether it returned a more complex structure implicitly, like a set of result channels. Has anyone ever done any Go programming? Yeah, so it's kind of similar to how you would do Tony Moore's CSP for coordinating across channels and green threads. Similar kind of conceptual model where, like, you would in that context you would inject channels, and that would be the set of result channels that you could signal out to, and then you would have a channel that represents your input channel. So you can represent this root concept in pretty much every different language. So the system definition is that there's sinks that are injected in, and so when this system receives a signal on one of its channels, then it's going to pop out to those. So now those become dependency injectable, they become unit test mockable, and all this. So I can exercise just the logic inside of here and not think about the subtleties of how data gets moved around and routed and dispatched and serialized and all of that other stuff. Oh yeah, so this was the thing that I've been wrestling with is when I look at, this thing is a sync to other systems, which is the input channel there, and it consumes and routes to internal sinks that were passed to it somehow. Should I use a union set to represent those things, or should it be a set of sinks that's more explicitly defined, or maybe like it's a generic parameter list, or a type that takes a variadic set or something like that. So that's a feedback point. If you guys play with this at all, get in touch with me and let me know what you think of it, and like what your thoughts on this, or talk about it now. like I said, dependency injection, so I can take this abstraction and inject the where does it go. So in a console environment, that might just be a function pointer to the next one. It's like direct dispatch, easy peasy. In the production environment, now that would expand out, and instead the runtime would be responsible for injecting a sync that, when dispatched to, serializes the message, puts it on PubSub, and expects PubSub to hit the router and dispatch out to the other things that need to act upon it. This doesn't feel super complex to me. This feels a lot like standard dependency injection stuff. So this might be too high level, but I'm trying to bridge those concepts across into the systems design space to figure out, like, has anyone worked with systems composition software? Like the simulation system software? So, like,
which one?
Just in general, I wouldn't look for different simulation system software to play around with and get more familiar with. And most of them were like kind of scientific oriented. There's a lot of drag and drop WYSIWYG stuff.
Oh yeah.
What I was missing, or what I was feeling I wasn't happy with, was that immutable infrastructure piece, where I could take the meta model that described what this composition looked like and apply it to their runtime. Do like a Helm chart apply into simulation system and have it be able to run that and describe that offline. But it was very proprietary, it was very in process. You define the thing and then you run it. That's kind of the feeling that I get from things like data flow, right? It's a very explicit operating model. You load the entire graph of data flow actors or steps into a data flow runtime, and it executes them in that runtime. But you can't take that data flow graph and then run it in the console, or they have tooling so that it runs their runtime on your local environment. But I couldn't say, like, take that graph and break it into chunks and then distribute it across multiple regions, right? And like maybe just like arbitrarily, compose, encapsulate a set of these things into a new one, and then reuse this encapsulated thing for another purpose somewhere. So, like, how do I program complex graphs of operating, of interacting simulations?
You sort of have something like that with Storm topologies.
Mm-hmm. Okay, yeah, and Storm has the bolts and spouts analogy. And so, in your experience, what is your experience with Storm? Does it hit on a lot of these topics? Are there any strengths or weaknesses that you can think of off the top of your head?
I don't think I would describe it that way. I mean, it's pretty simple, Okay. It's very stable. It's really nice for describing things like what you described, topologies of interconnected pieces, and then putting them out on a stable infrastructure, And the nice thing about it is you can distribute it very easily.
Okay, cool. Yeah, it's been a long time since I've looked at that, so I might have unknowns about the current operating model.
I would look at Heron instead of Storm.
Heron?
Yeah.
Okay.
Heron's like a re-implementation.
Perfect. Yeah, I'll definitely check that out. And those are language specific, right? It's like, it could be in Java or...
Yeah, that's right. Java and Scala. I think Python.
So you can use Arrow to run jobs in other languages like JavaScript.
Oh, okay. Interesting.
Yeah.
So it has like a runtime wrapper for other hosted systems. Interesting. It's really cool. Okay. Yeah, I was trying to think of like how could you, like if you took a Storm operational model, like a diagram definition, I don't know what to call it, the topology, and it could like compile, translate that into another runtime to say, like, because again, like how do you get that abstraction separated out so that like the description for what you're trying to do can be more generic, and then Storm becomes the runtime in which that executes with its own idiosyncrasies and like runtime constraints and SLAs and things like that.
I don't know enough about it, but I believe there is an Apache project that does that.
Oh,
yeah,
cool. If you remember to link
I'll
up,
share.
that would be really cool to check out for the group. And if anyone online has contributions, send them to Adrian, and he'll be able to get back to me.
Yes.
I'll make him responsible for all of it. So I might be reiterating something that's already covered by things like, you look at data flow has a compositional model that expresses these kinds of semantics. I know Storm does too. And so the abstractions that I'm thinking of are like maybe more generic, but follow the same compositional strategies. Cool. So that's it.
Cool.
Airflow.
Airflow. Yeah, I looked at Airflow. I didn't dig into it too much. I forget what it was that about that didn't resonate. But yeah.
The thing we were looking at Airflow for is we have too many cases. The only thing that we do with Jenkins is a scheduler. So it's like,
Yeah.
clear all the Jenkins are-
Jenkins is
get
like
rid of
the
those.
UI for Chrome.
That's it. Quotable. Jenkins is the UI for cron. Someone hashtag that for this event. Well, so I'll say